Hi everyone. Since we were clearly in a lot of different places today when I went over this particular problem from Wednesday's problem sheet, I decided to make you a quick video and show you a few details and let you absorb them at your own pace. First, a quick reminder of what's going on when we're talking about something like sodium methoxide. Remember, sodium, when it's bonded to oxygen, is an ionic bond, so you want to show this sodium plus one cation separate from your methoxide anion. And also remember that when we're talking about methoxide, what we're actually talking about is OCH3. Me is just short for a methyl group, OCH3. Remember that we are doing an E2 reaction, so we need to find our beta protons. Remember, our carbon with our leaving group is called our alpha proton. Our bromine is our beta proton. The adjacent carbon is what we call our beta carbon. And then what we want to look at is our beta protons, or the protons on those carbons. On this particular molecule, we have 3 beta protons right here. And we have 1 beta proton right here. And this one would be on a dash because we already have 2 bonds in the plane. 1, 2, 1 on a wedge. So that means this 4th group, this hydrogen, has to be on a dash. Now in this question, what we're clearly looking at is the elimination of this proton right here to make our 2 alkene products. This question is considering the stereochemistry of this reaction, not the regiochemistry. How we know that the beta proton we've pulled was this one is that the alkene we formed is this bond right here, meaning right here and right here. In this particular question, we aren't considering removing these protons, and I'll talk about why in a little bit, or why the reaction went this way. Quick clarification, there was a typo on this regarding which is the E and which is the Z on this stereochemistry. Looking at our priorities, first we're going to consider this carbon where our phenyl group is high, our methyl is low. On this carbon of the alkene, our methyl is high, our hydrogen is low. Since our highs are on the opposite side of the alkene, this is the Z. Since on this one our highs are on the same side of our alkene, this is the Z. Now let's take a look at how we consider the stereochemistry. The way the question is worded has actually gotten you started on how to think about the stereochemistry. It asked you to draw the 3 staggered conformations of the starting material. So thinking about the starting material, if I'm looking at the front carbon looks like this, with this methyl group being this one right here in the end. The hydrogen that's on the dash is right here, and the phenyl group that's on the wedge is right here. I'm going to change colors. What's on the back carbon is going to be the methyl sticking up. The bromine is out on the wedge, and the hydrogen is on the dash. And which hydrogen do I mean? I mean this one right here. Okay. Now I'm going to rotate my front carbon, and I'm going to draw my other 2 Newman projections. This is a situation where only one of our conformations has a proton that's anti-periplanar to our leaving group, and that is in this first conformation right here. What you notice in this conformation is that our leaving group is anti-periplanar to the methyl, so that's not going to be able to do an E2 elimination. And in this conformation, the bromine is anti-periplanar to the phenyl, so that won't be able to do an elimination. So these are our reactive conformations, these are our 3 staggered conformations of our starting material, and this is our reactive conformation, which is what we're going to take on to the next page and use to think about how to actually do this reaction. So here's my Newman projection. I'm going to bring in my OCH3, my methoxy group, to be my base. Sorry about that. I'm going to pull my anti-periplanar proton. I'm going to imagine that my bond is breaking and that my double bonds forming between my front and my back carbon, and my bromine is going to kick out. So the product that I'm going to get, if I'm thinking about the Newman projection, is going to look like this. So now if I take this out of the Newman projection, what do I see? I have the front carbon with its phenyl and its methyl on it, bonded to the back carbon, which is the one that's blue, that's got the CH3 group on it that's directly behind the phenyl group, and then in this case the hydrogen that's directly behind the CH3. And so this is going to be our product, and this is our high-low, high-low. This is our Z product. Thanks for watching, and I hope this helps.